two particles interacting via central force, now in 3 dimensions. Basic idea, we want to look at the motion, decomposing it into the center of mass and relative coordinates. Mass 1 with position r1 relative to some origin, and then mass 2 with position r2 relative to some origin. Therefore, we have 6 components. R1, 3 components, and R2, 3 components. We will define vector R, which is given as R1 minus R2, relative coordinate. And we will also define center of mass, capital R, which is given as 1 over total mass times m1 r1 plus m2 r2. Right away we can set capital R to 0 because center of mass is inertial reference frame. From r equals 0 we can find the small r, and we get r1 is equal m2 over m1 plus m2 small r, and r2 is equal minus m1 over m1 plus m2 small r. We can introduce reduced mass m1 m2 divided by m1 plus m2, and then write r1 as reduced mass divided by m1 times r, and r2 as minus reduced mass divided by m2 times r. Thus we can write Lagrangian first in terms of r1 and r2, kinetic term from first mass, from second mass, minus the potential of the force. For example, for gravity we will have u of r equal minus g m1 m2 divided by r. But we don't want to specify u of r just yet, so we are doing a more general case. We can rewrite kinetic energy as 1 over 2 r dot squared times mu squared divided by m1 squared times m1 plus mu squared divided by m2 squared times m2. Or, after simplifying, we get 1 over 2 r dot squared mu squared times 1 over m1 plus 1 over m2. And the parentheses are simply 1 over mu. So thus we get for kinetic energy simply 1 over 2 reduced mass r dot squared. So what kind of motion will these two particles perform? Well, it's easy to see that the motion is going to be planar. Planar motion. Because total angular momentum given by the angular momentum of the first particle plus the angular momentum of the second particle is conserved. As well as total linear momentum, P1 plus P2, is also conserved. Therefore, we can always go to plane of R and, for example, momentum P1 which is perpendicular to the angular momentum, and use polar coordinates there. When we do so, we will find the following equation of motion. Reduced mass times double dot of r is given by derivative of u with respect to r plus L squared divided by mu r to the third power. And then the second equation is the angular momentum given as mu r squared theta dot is constant. So we have reduced the problem from 6 dimensions to only 2 dimensions.